Hi everyone, welcome to my new video in my Mathematics Essentials series. This video is on polar coordinates. Okay, just an introduction to polar coordinates. Okay, so I'll give a few remarks about why they're important. Okay, why would we need to or want to ever work with some other kinds of coordinates if we already have coordinate systems that are pretty simple? Okay, well, turns out that if I have a Cartesian plane with an x-axis and a y-axis. Okay, so this is the Cartesian coordinate system, also known as the rectangular coordinate system or the xy coordinate system. Okay, if I pick some random point out here, let's call it P. Okay, see how I can drop a vertical line down to the x-axis and a horizontal line across to the y-axis from P, and this would define a rectangle. Okay, so that's why they're also known as rectangular coordinates. Okay, polar coordinates are different. So this would be rectangular coordinates if P just has some x and y coordinates that we express as these real numbers, whatever this x value happens to be and whatever this y value happens to be. Okay, now when you're doing calculus with some functions, okay, let's say you had a function like this. Okay, that was some function, y values equal to some function of x values. So you put some x value into an expression. Again, here are all your x values. Okay, so maybe you put this x value into the expression, and it turns out when you put it into this expression, it will spit out some y value over here. So you know that this point on the function would be there. Okay, you put in this x value, and it would spit out this y value. Okay, so you know that that would be this point on the function, which I tried to get close to the function. Okay, rectangular coordinates are good for functions that don't have any kind of circular symmetry. But with functions that have some kind of circular symmetry, okay, let's say we had a function like this. Okay, imagine that is a circular arc, all right, that would define some angle in here, right? But that angle is obviously going to be 90 degrees or pi radians, okay? When we are doing calculus problems on a kind of function like this, y equals f of x, it turns out that polar coordinates are going to be much easier to work with than rectangular coordinates. So what are polar coordinates? Well, you remember that from our unit circle definition of cosine of theta, that it's equal to x, right? And that sine of theta is equal to y. But that is only when we're talking about a unit circle. Okay? So actually I'll draw the circle first. So let's say we have some circle. Oops. And then we're treating the circle on an xy coordinate system. Okay? Right, we know that this, that if we take any point on this unit circle, we know that the line from the origin to that point is going to have a radius, which I'm denoting by lowercase r, equal to 1. And that this point here, let's call it P, right, it will have x and y coordinates, but they will be equal to the cosine of theta and the sine of theta respectively. Okay, well, these only hold when our x and y coordinate point is some point on the circumference of a unit circle. Okay, so long as x, the x value, right, and the y value get us some point on the unit circle, which has a radius of 1, then the cosine of theta is equal to x, and the sine of theta is equal to y. Okay, remember, we can interpret this as defining a right angle triangle with an angle of theta here, measured anticlockwise from the positive x-axis. Okay, then cosine of theta is going to equal x and the sine of theta is going to equal y, but what if we are dealing with points that are not on a unit circle? Okay, well, that would correspond to right angle triangles which have a hypotenuse that are greater than 1 or less than 1, or you can think of it corresponding to circles for which the radius is greater than 1 or less than 1, so non-unit circles, just any other circles other than unit circles. So it turns out that the cosine of theta and the sine of theta are not going to equal x and y respectively in those cases, because remember, our unit circle definitions for these trigonometric functions have to respect our right angle triangle definitions. Okay, these do on a unit circle because the cosine of theta is equal to adjacent over hypotenuse, but the adjacent side to theta is just some x value, right, over hypotenuse, and the hypotenuse on a unit circle is just 1. Okay, and for sine of theta, okay, the unit circle definition respects the opposite, which is just some y value over the hypotenuse, which is just 1. Okay, so sine of theta is going to equal y as well, and cosine of theta is going to equal x still. Okay, they respect our unit circle definitions. Okay, I just want you to note here, okay, you'll see why I'm doing this later, but if I multiplied both sides by 1 in each of these equations, okay, you could just write 1 equals to, cancel on the right, and you'd have 1 times the cosine of theta equals x, again, y equals 1 times the sine of theta. Okay, interpret this as some radius times the cosine of theta times equal to some x value, and interpret this as some y value equal to the sine of theta times some radius, because that's the form that polar coordinates are going to have when we scale this up or down. So when we scale our right angle triangle, we'll get to some other point out here, okay, which we call A, okay, and it's going to have some x and y coordinates. Let's not worry about what they are right now, okay, but notice that, okay, if I draw another diagram because that one was getting messy, I'll draw a Cartesian plane. Okay, x-axis, y-axis. Okay, imagine that we scaled this up. Okay, so, or we scaled it down. I'm going to imagine that it's scaled up. Okay, in this case, all right, when we draw a line from the origin to some point, okay, remember this is scaled up, so the point P, this point here, would be, let's say, like, somewhere like that, for instance. So it would be somewhere along our line, okay? Let's say we drew it out to a point on the Cartesian plane, so we extended that line from the origin to P even further, we'd get to some other point A, right? And I'm going to just give it some x and y coordinates, because it will have some, okay? Now, because we've scaled things up, this line here no longer has a radius of 1. It's got a radius greater than 1 because this is no longer a unit circle, which means thinking of this as a right angle triangle, what's going to happen is that our right angle triangle is no longer going to have a hypotenuse of 1. Okay, so this hypotenuse, which I've called h, you can equally think of as the radius of this circle, okay, which I'm denoting by a lowercase r. Okay, and since our unit circle definitions of cosine of theta and sine of theta have to respect our right angle triangle definitions, well, this here is the opposite side to our angle theta, which hasn't changed under scaling, and this here is the adjacent side, so that would be opposite, okay, which would be equal to whatever this y value is over here, which would be the y value of A, and whatever this x value is over here, okay, so that's what the side length of the adjacent side would be, which would just be equal to whatever the x value of our point A is, okay. Notice now that the cosine of theta is going to equal adjacent over hypotenuse, because that's the right angle triangle definition, okay, but that's not going to be x because we're not dealing with a unit circle anymore, okay, so adjacent is going to be x, okay, over the hypotenuse, right, which we can treat as r, the radius of some circle, and now if we multiply, well, firstly, we can see that the cosine of theta doesn't equal x anymore, okay, it equals x over r. Okay, so the cosine of our angle theta equals some x value over whatever the radius of that circle is, which is not a unit circle. So what we can do is times both sides by r, and we will get r times the cosine of theta equals x. All right, now for sine, okay, the sine of theta would be equal to the opposite over the hypotenuse. Okay, but the opposite side to our angle theta is just a side length of y, and over the hypotenuse, which you can also interpret as r because the radius of that bigger circle, which is not a unit circle, okay, sine of theta no longer equals y anymore like it does on a unit circle. Okay, but if we want to isolate y, we would just times both sides by the radius, and that would cancel on the right hand side, and we'd be left with r times the sine of theta is equal to y. So we can see that no longer does x equal cosine of theta and y equal sine of theta. X is equal to some radius times the cosine of our original angle theta, okay, and y is equal to some radius times the sine, okay, of our angle theta. So now what we can do is our point A, which had Cartesian coordinates or xy coordinates or rectangular coordinates, those are all names for the same kind of coordinates, okay, it had coordinates x and y, okay, we can express as r times the cosine of theta as the x component, and we can express the y component as r times the sine of theta. Okay, and you can see that that would get us any point on this bigger circle. And the same kind of reasoning, any point on the circumference of this bigger circle has been scaled up. Okay, and the same kind of reasoning would apply if it's been scaled down. Okay, it's just that the radius would be smaller than 1 rather than greater than 1. And this here is what it means to express the coordinates of A in polar coordinates. So that's polar coordinates in a nutshell. So if you found this video helpful, give it a like. Feel free to share it with your friends. And if you would like a notification when I upload a new video, subscribe to my channel. And if you have any questions, post them in the comments as well. Until next time, bye for now.